In this video, we're going to take a look at the tools we need in order to solve linear equations in one variable. Let's take a look at some of the big ideas surrounding why we might want to solve linear equations in one variable. These equations can model real-world relationships between quantities. When we solve an equation, what we're doing is finding any values that make that equation true. In order to do that, we'll find that what we're going to do is use the opposite or inverse operation to undo an equation. You'll see more about what I mean by that as we go through these. Linear equations form the foundation of algebra, and once we know how to solve them, we'll see we have some tools that help us solve lots of different types of equations. In order to be able to solve linear equations, we need to be able to recognize them. So we'll start with a few definitions and some structure around linear equations. First of all, a linear equation in one variable can be rearranged so that it takes the form ax plus b equals c. In this form, a, b, and c represent different numbers. X is our variable. It's the only one we have in this equation. And notice that x doesn't have anything happening to it other than potentially being multiplied by the number a. In other words, in a linear equation in one variable, we'll only have one variable x. We'll see other equations later where we add additional variables. And that x is raised to the first power. We won't see things like x squared, or the absolute value of x, or the cube root of x inside an equation that we identify as linear. We'll define the solution of a linear equation to be the value of x that satisfies the equation. In other words, once we're done solving, we can take the answer we got, we can plug it back in for x, and we should get a statement that is true. Our whole goal when solving is to isolate the variable. We're looking to find what x equals. So what we're going to do is use algebraic tools in order to rearrange the equation so that x is all by itself on one side, and we end up with a number on the other side. Let's start with a pretty straightforward example in order to demonstrate how this works. Here we want to solve 3x plus 5 equals 20. So we're looking for the value of x that when we multiply it by 3 and then add 5 to it, we get 20. Our goal is to get x all by itself. We can see that there are two things happening to the x in this equation. It's being multiplied by 3, and then that quantity has 5 added to it. We're going to use opposite or inverse operations in order to reverse that. In general, a good rule of thumb is to start with the operation that is the furthest away from the x. So since the 3 is right next to the x, we're going to hold on that for a second, and we're going to get rid of the plus 5. The opposite of adding 5 is subtracting 5, so we'll take 5 away from both sides of this equation. When we do that, on the left-hand side, we're just left with 3x, and on the right-hand side, we have 15. Now we can see that the only remaining thing happening to the x is that it has a 3 multiplying it. The opposite or inverse of multiplication is division, so we're going to divide both sides by 3. The 3's cancel on the left, leaving us with just x. And on the right, we get 5, 15 divided by 3. We can check this. Checking means take the value for x, plug it back in. So we get 3 times 5 plus 5 on the left-hand side. Well, that's 15 plus 5, which is in fact 20, the thing we had on the right, and so our equation checks. Let's try another one. Here we have 4 times the quantity x minus 2 is equal to 10. Those parentheses provide us with an interesting challenge. We have to remember that that 4 is multiplying everything inside of those parentheses. In other words, we have 4 copies of x and we have 4 copies of negative 2 on the left-hand side. There's 2 approaches we could take. The first is to use the distributive property. I'm going to try that one first. So I have 4 times x minus 2 equals 10. I'm going to distribute that 4 inside the parentheses to get rid of them. That gives me 4x minus 8 is equal to 10. Now this looks a lot like the example we did previously. So we can add 8 to both sides. We have 4x equals 18. We can divide by 4. And we get x is equal to 18 over 4. Both of those are even numbers. We can divide them both by 2, so we get x is 9/2. And if you prefer a decimal, you can write that as 4.5. We'll check that in a minute. First, I want to look at a second way to solve this. Starting off with the same equation, another choice we have would be to divide both sides by 4. When we do that, those two 4's cancel, and we're left with x minus 2 is equal to 10/4, which is the same as 5/2, since both can be divided by 2. I don't really need the parentheses I wrote there, so we have x minus 2 equals 5/2. Now we can add 2 to both sides. Now, of course, we're in a position where we have to remember to rewrite 2 so that it has a denominator of 2, and we get that x is equal to 9/2, or 4.5. We got the same answer both ways. Let's check our answer. And again, we're going to do that by replacing the x inside of the parentheses with 4.5. So we have 4 times 4.5 minus 2 on the left. That's 4 times 2.5, which is in fact 10, and our solution works. Our last example had a fraction in the answer. Let's look at a more complicated example that has fractions in the problem itself. One of the easiest ways to deal with a problem like this is to think about what the common denominator for all of those fractions are. So here we have 3, 6, 2, and 4 as the denominators of our fractions. The lowest common denominator of those is going to be 12. The smallest number that each of them divides. 3 times 4 is 12, 6 times 2 is 12, 2 times 6 is 12, and 4 times 3 is 12, and there isn't a smaller one. What we can now do is we can multiply the entire equation, multiply all of the terms in there. I don't think that's how you spell multiply. Let me try that again. Multiply all the terms by 12. What this is going to do is clear the fractions. It's going to make them go away so we don't have to continue with them and we don't have to worry about common denominators anymore. As long as we do this to every single term and we do it on both sides of the equal sign, our equation won't change, its solutions won't change, and we're doing something that's legal algebraically. So I'm going to take 12 and I'm going to multiply it by the entire expression, 2/3 times x minus 4 plus 5/6 times x equals 1/2 times 3x plus 1 minus 7/4. Now, it's very important, since I said that we need to multiply by all of the terms, it's very important that we know what a term is. So inside of an equation, terms are going to be separated by pluses and minuses. So in other words, this is a term. Then we come upon a plus sign. So then we have another term. Then we have the equal sign. That also separates terms. Over here, we have two things multiplied together. That makes our third term. Then we have a minus sign, and we have our fourth term. So this equation has 4 terms in it, each of which needs to be multiplied by our 12. So in other words, we're now going to distribute this 12 to the first term, the second term, the third term, and the fourth term. So I get 12 times 2/3 times x minus 4 plus 12 times 5/6 of x equals 12 times 1/2 times 3x plus 1 minus 12 times 7/4. Now the beauty of our choice in 12 is that it's going to cancel with each of the fractions we currently have so that we end up with an integer. That's why we chose the common denominator. So when I multiply 12 times 2/3, the 3 and the 12 cancel to give us 4, and there we end up with 8 times x minus 4. In our next term, the 6 and the 12 cancel to give us 2, and we end up with 10x. In the next term, the 2 and the 6 cancel to give us a 6, and we get 6 times 3x plus 1. And then in the last, the 4 and the 12 cancel to give us a 3, and so we have minus 21. Now we have a problem that no longer involves any fractions. We can use our techniques from previously to solve these. So we'll distribute the 8 and the 6 into the parentheses. We get 8x minus 32 plus 10x equals 18x plus 6 minus 21. Now we're going to do something we haven't really talked about. We're going to do what's called combining like terms. So like terms are ones that have the same variable to the same power. Now, we're only dealing with linear equations right now, so all the powers of our x's are going to be 1. So any term that has an x in it is going to be like every other term that has an x, and any term that doesn't have an x will be like any other term that doesn't have an x. So let's look for our like terms here. We have 8x and a 10x on the left. Those can be combined. 8x plus 10x makes 18x. On the right, we have a 6 and a 21. Neither one of those has an x in it, which makes them like terms. And so now we have 18x minus 15. I forgot to write the x in that. Let me fix that. 18x minus 15. Okay, now, if you have any experience before solving equations, you might be starting to get a little suspicious about this one. But remember, our goal is to isolate the x. So we want to get all the x's on one side. So what I'm going to do is I'm going to add 32 to both sides. On the left, that gives me 18x equals 18x. Negative 15 plus 32 is positive 17. We have an x on the left and an x on the right. We're going to move one of those over, so I'm going to subtract 18x from this side. And now here's where we start to see something very strange. We get 0 is equal to 17. Well, that's nonsense. This is a completely false statement. What does that tell us? Well, that tells us that our original equation has no solution. In other words, there is no value of x that satisfies our original 2/3 times x minus 4 plus 5/6 of x equals 1/2 times 3x plus 1 minus 7/4. And the way we recognize that is that we do all of the work to solve it, and then we end up with something like 0 equals 17, some mathematical statement that makes absolutely no sense, which we know for a fact is false, and that tells us that our equation has no solution. Let's take a look at one more example, this time involving decimals rather than fractions. We can do a similar trick. We can clear the decimal. We can see here that we've got a 0.75 multiplying our first term. So again, we're going to be thinking about terms. We've got one term here, one term here, one term here, and then one term here. I've written that kind of poorly. That should be a negative sign there. And so we can see in each of those, they involve a decimal. We've got a 0.75. There's also a 2.4, but it's inside the parentheses, so we're not going to worry about that quite as much in the first term. Then we've got a 1.6, a 0.5, again, a 1.2 in the decimal that we're not going to worry about right now, and a 2.75. Since the 2.75 and the 0.75 have two decimal places, that tells us tells me what I want to do is multiply by 100. Multiplying by 100 is mathematically equivalent to moving a decimal place 2 to the right. So when I do that, I'm going to multiply 100 by everything. So I do 100 times the first term. 100 times 0.75 is 75. The 100 does not go into the parentheses. This entire expression is one term, so it only gets one copy of the 100, and I used that up when I made the 75. So I'm done with the 100 now. I don't need it again. Now I'm going to multiply the 100 times the 1.6. Moving the decimal place 2 to the right, I get 160x. Now I'm going to repeat that, multiplying into my third term. Again, 100 times 0.5 is 50. I don't bring the 100 into the parentheses because I used it up when I multiplied it by the 0.5. And then lastly, 100 times 2.75 is 275. I forgot a decimal point when I wrote this in here, so I'm going to add it in. This should be 1.2. Be very bad in a few minutes if I forgot that. Now I'm going to distribute the 75, so I get 75x, and then I have 2.4 times 75. Can't do that in my head, so I'll just do it over here. Let's do an old school multiplication here. I get 1800, and I have one decimal place, so that's going to be 180. So I get minus 180 plus 160x. On the right, I'm distributing the 50 now, so that's going to go to these two here, and I'm going to get 150x. And then I have to do 50 times 1.2. Well, that one I do know, that's actually 60. You can check that on your own. And then I'm going to do minus 275. All right, now we're in the place where we're going to combine our like terms. So let's look for like terms. On the left, my like terms are 75x and 160x. They both have x's in them. So we add those together. 160 plus 75 is 235x minus 180. On the right, my like terms are the 60 and the negatives 275, which is negative 215. So I have 150x minus 215. Now I'm going to move this 180 over. I'm going to add 180 to both sides. That gives me 235x is equal to 150x. 15 minus 25. Nope, 35. And then I'll subtract 150x from both sides. Again, remembering that our goal is to isolate the x, so we need it all by itself on one side. This is going to give me 85x equals negative 35. Then we're going to divide both sides by 85. So I get negative 35 over 85. We started off this problem using decimals, so we want to end it using decimals. So we're going to divide 35 by 85, which is a very, very ugly looking decimal. So we can either leave it as 35/85, which we can this simplify. So if we divide everything by 5, we get negative 7/17, which is approximately 0.4118. We have to round that decimal. It comes out to be irrational. Not irrational. It's totally rational, but it comes out to be a very long decimal, a repeating decimal. So we can round it to 0.4118. We've seen a lot of techniques that we can use when solving a linear equation in one variable. So let's take a quick summary of those. Linear equations can be written in the form ax plus b equals c, where x is the one variable we're talking about. These equations have a single solution, or we also solve that sometimes they have no solution. Solving means isolating the variable. In order to do that, we're going to use opposite or inverse operations to undo an equation. We saw that sometimes clearing fractions by multiplying through by an LCD or clearing decimals by multiplying by some power of 10 can make our life easier. And we also saw that checking our solution can help us to verify our work.